Hello everybody. These are official notes on vector projections. So I believe we left off somewhere around 10 in our notes. You can kind of pause this video as you go along, catch up as you need, rewatch it, whatever you'd like. So I'm going to assume that this is topic 10 here, or topic 11 now. And this is going to be vector projections. What we're going to be looking at here is the projection of a vector u onto a vector v. The way we denote it is by projection abbreviated PROJ of u onto v, like that. I'll leave this blank for a little bit and we'll get the official formula for this in a second. But first, here's essentially what it is. So if we have a vector v here, and then we have a vector u somewhere out there. What we're looking at here is the projection of u onto v. So if we were to kind of take this vector and talk about how much of an impact it has on v in v's direction, what would that vector look like? Now, because we're projecting it onto v, there will be some magnitude of this direction. So this direction will be the answer. It's just a matter of where along that vector it is. It could be here, it could be up there, it could be back. So ultimately the way to do it is by drawing a right angle with vector v, and then this part right here is the projection of u onto v. So the official formula, do it in green here, is going to be some scalar times vector v. It's because it's along this line, just some part of it. And for a variety of reasons, mathematically, this is ultimately the formula that's used for it. It's the dot product of u and v divided by the magnitude of v squared. We're going to take a look at a horizontal one first. So our first example is, imagine if vector u was 4, 3, and vector v was 10, 0. Let's take a look at what this looks like. So vector v would be going out somewhere like that. Vector u, 4, 3 over 4 up 3 might look something like this. The projection of u onto v is ultimately just going to be the horizontal component of this vector. So we know that it's going to be 4, 0 without doing any math, because it's a straight horizontal line and the part attributed of u to v is 4, 0. Here's the math of it. If we actually do out the dot product of u and v, we would get 4 times 10 plus 3 times 0, so u dot v is just 40. The magnitude of vector v is just going to be 10, so divided by 10 squared, times vector v 10, 0. So this is like 40 over 100, which is 0.4. So it's 0.4 times the vector 10, 0, which gets us 4, 0, which we already knew was going to be the case, because in a straight horizontal line situation, it is just going to be the x component of u, since that is what is projected. Where it gets a little trickier is when you start to use ones that are at an angle. So here's an example of that type. So example 2. Let's say now that u is a vector 6, 10, and v is a vector 8, 2. So what this would look like, we'll do vector v first. 8, 2, 1, 2, 3, 4. So 8, 2, be a vector that looks something like this. I'll label that v. Vector u at 6, 10 would be out here, then up 10. So it would be going something like that. In order to find the projection of u onto v, we could just use this formula, the dot product of v, u and v divided by the magnitude of v squared times v. When I'm looking at this, I'm thinking it's going to be pretty close to the vector v itself, since if I try to draw an altitude there, it looks pretty close to where vector v finishes. But let's find out exactly. So the projection of u onto v, start off with a dot product, 6 times 8 plus 10 times 2, divided by the magnitude of v squared. So if we do Pythagorean theorem here, it would be 64 plus 4, that's 68. The magnitude is rad 68, but we can actually just call that 68, which you'll see shortly. Because if we square it, it just ends up being itself. 8 times 6 is 48 plus 20. So we end up with 68 over 68, how about that? Times the vector 8, 2. So it turns out in this case that I was pretty accurate with that. It ends up actually being vector v itself, 8, 2. Will not always work out like that, but whatever this was, you just multiply to both of those components. Okay, good luck on the 2 problems, and more to come tomorrow.